Hi everybody, my name is Vikram, and we will be today going over machine learning end-to-end from the very beginning to hopefully keeping it a cycle. My name is Vikram, and I run a startup called Omni Labs. I'm based in San Francisco, and I'm also a Google developer expert for Google Cloud as well as machine learning. So if you have any questions around cloud, machine learning, feel free to shoot at me. I'll be here after the event as well. Presentation is actually very long. This presentation is a 4-hour workshop format, but hopefully let's see how quickly can we get through it. All right, we are also hiring. Omni Labs reached out to us on angel.co/omnilabs. Yeah, my email is right there, Vikram@Omni Inc., and we are hiring. All right, so machine learning. How many of you seen Matrix movie? Nice, some, few, nice, that's good. Matrix starts with Neo not knowing anything, and later it becomes this. Oh, not too much, this. Neo goes on to say, yay, I know Kung Fu now. All right, so that's what we're gonna try to do today. We're gonna start with knowing nothing and hopefully come out with knowing something. So every technology that we see overall come up has this trend where the technology trigger happens, there are inflated expectations that happen, and then everybody is like, this is not gonna pan out, something that is happening with VR right now, something that is happening with blockchain right now. But yeah, similar things happen. I think for machine learning, we are right here. Like we haven't even understood, our expectations even haven't been inflated yet. There are so many things that are happening right now which are like very much in progress. And we will see where we go. There's also a concept of AI winter, which already happened, still too many things. But as I see it, we are right here. So what is machine learning? How is it different between all the terms that get thrown around all the time? So what is AI? AI is just making a machine solve any problem that humans are trying to solve, but in a more, that is associated with human intelligence. That's general term for AI. People have been doing AI for a long time. People were writing rules to do that AI. But now we have machine learning. With machine learning, you make a machine learn from experience rather than encoding human experience into the machine. So that's how it's different from AI. And then deep learning. Deep learning is one very small subset branch of machine learning, where you use deep neural networks. Deep neural networks modify or codify how human brain works. And they're just trying to emulate that to do the machine learning part. AI, machine learning, and deep learning, that's how they are different. They are not the same thing. Okay, so how is it different from the programming that we all know and love? So let's say if you were to build a machine learning model for detecting a movement, how would you do that? In traditional programming, what you can say is you have a variable coming into you, which is speed. And you say, okay, if its speed is less than 4 miles an hour, the person is walking. If it's greater than 4 hours, that's the first case that you got. The next day you see, somebody is actually walking faster than that. What is that case? So you say, okay, this is running, if it's greater than 4. Then you say, okay, I also want to include new feature in here where people might be biking. So how do I do that? You add third case in here. If it's less than 12, it's running. If it's more than that, the person is biking. But what about this? Now you need to capture so many features. What do you need to write? The code becomes too complex for you to understand or come to a proper conclusion even, whether this code is correct or not. That's how traditional programming works. So traditional programming is you have rules and you have data, you pass it and write your code, and it gives you answers. Machine learning is just a bit different. You already have your answers, you have your data, and you train a machine to understand that data and then give out rules. So until now, we have been coding rules. Now, machine gives out these rules that we now use later for our problem. So how does this work in our problem? So you get some data, you label it as walking. You get another set of data, you label it as running. Another set of data, biking. Too fast. Too fast. Another set of data, which is golfing, sort of. Okay, so how is machine learning different? You get answers and data, you pass it into a machine learning model, and it gives you the rules. What is this machine learning model? How does it look like? So there are various forms of these machine learning models, but essentially when you get the model, you pass your data in, the new data that you want to make predictions upon, and you get new predictions. We will talk more about model now. So the difference is the first phase is called training, the second phase is called inference. That's the basic difference between these phases. Okay, but why should I care about machine learning? Mostly because there's a revolution going on. There's a revolution going on in machine learning, and they are changing everything that we do. This is association between Google and NASA, and they were trying to find out new planets, new exoplanets around the sun, around like other planets' sun. Those are called exoplanets. And NASA has done a lot of research. They have found a lot of planets based upon their telemetry data that they get from their all these services that they have on the space. They have already identified a lot of these. But with machine learning, what Google and NASA in collaboration were able to identify are these new planets which they were not able to identify until now. And this was like very well done. So this is Kepler-9t system that they were able to identify, which is same as understanding, okay, when a planet is going around the sun, when it is behind the sun, you see a very high intensity come up of light. When it's in front of the sun, you don't see that. Next is image recognition on the retina of the eye. This is an experiment that Google AI team is working on, and with Alphabet's team, Verily, they are working on this now. This data set initially was used only to understand diabetics, of like a person is diabetic or not, using the retina of the eye. But they gave it to one of their new interns, and she was able to identify 18 new features out of that. So they are now able to identify 18 different diseases just by looking at your retina of your eye, just this image. This is non-invasive method of doing all of these detection of your diseases early in your disease cycles. Next, these are not only efforts that are being led by big companies. There are grassroots efforts on machine learning which are also happening. These are some people who were against deforestation. They built machine learning models, put them onto older Android mobile phones, hung them onto trees, and whenever there was logging happening into the forest, those models captured those logging sounds, sent an alert that there's a logging happening here, and if it was not approved logging, it sent an alert to authorities. Authorities would go there and stop that. And this is all grassroots effort built by some researchers and some team which was working on this problem. Then, machine learning is not only focused upon things to solve, it's also trying to do imaginative stuff. This is Project Magenta. Magenta project is focused upon generating music. Generating anything is hard. Generating music is super hard because you can generate a tone, but when we are talking about music, you have to understand what was the history, because you might be out of tune then if you don't understand the history. So it's like very big models that become and generate these things. And this is already in production. Google has put out this device called End-2-End. And End-2-End, if you have seen Google I/O demos for the last 2 years, they have been using these onto the stage when they do the initial prep-up of the event. Okay, but what about actual usage in production? So best example for this is Google, and you see Smart Compose. How many people use Smart Compose all day? I can't write email without a Smart Compose anymore. Google Translate, where you can do in real-time translation. They have AI kits. They are working so much on these that they had to build their own hardware for this. TPUs, we will talk about that in a minute. All right, so what is making all of this possible? That's TensorFlow. TensorFlow is one programming language, platform, whatever you want to call it. It's evolving so much that one definition doesn't fit it anymore. TensorFlow is making all of this possible. How? So TensorFlow is a machine learning platform for everyone to solve all kinds of problems. And when I talk about everyone, it is everyone. People from all over the world. The only place remaining is Greenland. Somebody please go there and make a commit from there so that we can have that on the map. But people from everywhere in the world are using TensorFlow. What is TensorFlow? TensorFlow is basically the language paradigm which you use to solve multidimensional array problems using a graph of operations. So there's a multidimensional array, which is the representation of your data, and tensors, which is the representation of your operations that you want to perform. So how does this look? This is your data. So your data could be in different formats, but machines only understand binary. So what you end up doing is you end up codifying your data into binary format. So for an image, this is one of the easiest examples to convert an image. You take an image, you make it grayscale, anything that has color, which is any point from 0 to 255, you give it a number from 0 to 1, and anything that doesn't have any value, which is white, you make it 0. So your 1 looks like this in a matrix format. Similarly, what is tensors? Tensors are operations. So any operation that we do in here you will see there are a lot of operations that are happening, and the operations pass data to each other. This becomes the graph. So tensors are your data units, and this is the graph of operations. Graph of operations are really important because it provides the TensorFlow ability to train anywhere, run anywhere. Just the same way JVM used to do. JVM revolutionized how we used to build application earlier. All right, so how does this work together? You take an image, you train it. By training, we mean an input layer. Input layer is a set of neurons. All of these things, this is like very basic description of how a neural network works. A neural network is made up of a set of neurons, a set of layers, and each layer learns a different type of understanding, or like whatever the image is trying to codify. And we have demos for this. We'll do if we have time. And in the end, you finally get an output layer. From there, it can do the classification of whether this is a cat or a dog. And this is deep neural network. OK, so how do I get started with that? First of all, what we have to do is we have to define our problem as a machine learning problem. This is what people end up doing wrong. People just start using machine learning without understanding whether their problem actually fits into a machine learning problem. So what you have to do is understand what is your problem and define it as a machine learning problem. So our problem here is I want to understand whether a user wants to go to a hike or not. So that is our problem. The likelihood of going to hike is 1. If it is 1, then user wants to go to a hike. If it's 0, user doesn't want to go to a hike. And we're trying to classify that. So you end up getting your model, and like this is your problem. Now we want to break that problem into different parts for machine learning. First, we have labels. Labels is your raw data that you get, on which you will train to get your actual final model. Then we have our features. Features are small sets of things that you can understand from your data, basically features, what the English word means. So you understand, OK, what are the features of hike? How tall is the mountain? What is the weather? And then user features. User actually wants to go for a hiking. User has shoes for hiking. Or they have the raincoat. If they don't, they won't go. Models. Then model part we will talk about in detail in a minute. But finally, when we build the model, we get predictions out of that. Predictions are actual likelihood of going to that. It's not one-off result. It's not yes or no. It's always a likelihood. So it's likelihood between 0 to 1. It's like you can convert that into a percentage easily. OK. So I have data. But what if I have very small set of data? What if I want to generate more data out of that? Or my data is very randomly distributed. Or my data is just randomly in here somewhere. How do I start feeding the data into my machine learning model? For that, you have to make sure that your data can fit into these forms. One of those is called bucketing. So for bucketing, you can say, OK, I have age ranges for my users. Every user has a range. But every user has an age. But I cannot simply put all the age values in there, because it won't matter. It really doesn't matter if you're 26 or 27 for you to go on a hike. So what we end up doing is we end up bucketizing them. We separate them as youngs, adults, kids, things like that. So that becomes buckets. Then feature crosses. Feature crosses are you are a male and 27 years old versus you are female and you are 18 years old. That very much depends on whether they want to go for a hike or not. So at that point, you end up creating cross features. Then there's hashing. Think of everybody's addresses. You cannot really create a feature out of address. But if you end up hashing them, then it becomes a feature. Because what ends up happening is you end up assigning a binary number to the address. Everybody's address is different. Everybody's address gets encoded differently. That becomes hashing. And then one of my favorite is embeddings. Embeddings are so cool. Embeddings are a representation that model has learned about the data. So up till the 3 features that we talked about, we are creating those features. But embeddings are the features that model learns about the data, and you can reuse those features. Google uses these in their natural language translation models, where they trained model on X to Y language and Z to A language, and their model, the embeddings that it learned, were useful for every other language. So they can just reuse those embedding features everywhere else. So embeddings are one of the harder concepts. When you are doing this, you will find that embeddings are really, really useful. All right, next, I have my data ready. How do I actually get started with using the model? What is the model? OK, so for that, TensorFlow provides you various ways of using the model. But what I suggest is start with pre-made estimators. Pre-made estimators are somebody who built a model for you already, all ready for you, so that you can just get started with that model. So all you have to do is take the model, pass in your data, and you get your results out. Next is estimators. You can use estimators to train on your data. So first one is complete model trained for you. You just have to pass in data to get inferences out. Second one is estimators that you have to train upon your data. Then third, as we go lower, we will see more complexity arise. So third is TF-Keras. TF-Keras is to build your own model using some approaches that are already understood in the community. So you want to use a ReLU, you want to use an activation layer, you want to use a softmax. All of those are available for you in TF-Keras. Then comes TF**. TF** is like anything inside TensorFlow. These are very important for researchers. Researchers don't care about what you have already built. They want to invent new things. For them, they start on the very low-level APIs, TF**. What I see people doing is people start with TF**. Don't do that. You don't need to learn the language. There's no need for you to learn the programming. If you can utilize an existing model, do that. OK, how do I utilize an existing model? So TensorFlow has a very, very well-defined thing called transfer learning. This is a concept which we use all the time now. One of the best models out there for natural language translation is BERT, B-E-R-T. And that BERT model, all it is just an encoding. And you pass in your data, and it uses the learnings that it has from other data sets to encode into your data to give you a new model. And that is transfer learning. With transfer learning, what you do is, whatever you have learned from one model, you can remove some layers out of that, add in your data, and it is ready for you now. I have a very good example around this on GitHub, where we take an image model which Google had trained upon millions of images for days. We take that model, we remove last layer, train it on images of noodles, and in 10 minutes, I guess, we have a new model which works on 3 categories of images. And you can take that model, you can run it on your own categories, and it will be ready in 10 minutes on your machine, trained on your machine. So you don't have to build or understand all of the conceptual history behind this to utilize this. So it just transfers the understanding. Second one is implement one of the popular models. This is a language translation model. I don't remember what this is called, but this is a natural language translation models. People have done years of research into coming up the best way to do things. You don't have to reinvent the wheel. Just use whatever they have done. You might even find Python code for this. You might even find the whole TensorFlow code for this available online. Just utilize that. There's no need for you to understand the whole thing. Understanding is good. Do that if you want a career in machine learning. But if you want to utilize machine learning, you don't have to. All right, then experiment with wide and deep models. Right now, there's a hype going on. I wouldn't say hype. Those models are really good. Deep models, everybody's preferring deep models. Deep models end up giving you a lot of understanding from the data that you might not have by yourself. So deep models have the quality of understanding data way better than humans would. But there are some data sets that you might know well. Like if it's your users, or if it is your community, you might know your community much better than the data that you have available from your community to get a model those signals. So those are the signals that you will codify by yourself into a wide model. Wide models are the models where you codify your features, versus deep are the ones where model understands those features from the data. OK, experiment with both of them. OK, what is a model function? How do I get started by writing that model function? So a model function is basically a collection of few things. One is the features that you define, then the network that it creates, and finally the head that you use for predictions. So let's break it down. So let's start using it by saying, OK, how do I use this? You have a set of features that you started. So the image is reversed now. You pass in your data. Those come into as features. At each pass, you compute the loss. Loss is this. Loss is saying, how bad did your model do? So if I had a model to predict a line, how bad was my model on understanding what is that line and where does that line go? What you do is, your aim is always to reduce the loss. So you do iterations. On machine learning, it's very important to do iterations. You cannot have a good model in one single pass. So you do iterations, and every time your aim is to calculate the loss and minimize it. You always calculate the loss, and you end up minimizing it. So you keep doing this iteration until it comes to a point where you are happy with your model. If your model converges to 100%, it's wrong. Do something else, because something else is wrong in there. Your model should never go to 100%. All right, so this is loss. Loss is saying, I start at a random point, and I try to go to a point where my error is minimum. And you go to that loss by decreasing your parameters. If you want to understand all of these, this slide will be shared. There are notes in there. They are linked to workshops and like the Colab notebooks. We'll talk about that. And you can do all of these things on your own. OK, how do I actually write that model? So for that, people used to do a lot of different things. But now the best suggested way out there is using Keras models. So you start using tf.keras. OK, so to build that model, you don't have to understand this code. But what we are doing is we take one sequential layer, and we add two layers in there. One sequential model in which we add 2 layers, one with 64 neurons, one with 10 neurons. And then we compile that model using an optimizer. Optimizer helps us reduce the loss. And there's a loss computation, which we calculate using categorical cross entropy. Don't have to worry about these things. You can learn about this later from all the links that we have in here. OK, so that becomes our model head and network. OK, but how do I take this out? To take the model out, you have to use estimator, convert it to an estimator. When you convert a model into estimator, it gives you a few things. Few things saying, OK, you wrote your model, but now with packing it into an estimator, we give you a few easier ways of approaching that model or giving that model out to other people. How many people are familiar with scikit or similar other platforms, scikit or XGBoost? What they do is they give you few functions on training. You have a model, you just pass in model.train and pass in your data. So estimator gives you that ability directly. Then it also gives you evaluate, which is used to understand how well your model is doing. It also gives you predict, to predict the model. But one of the best things that it is doing, it's also giving you export saved model. By exporting saved model, what you can do is you can take your model that you trained on your machine and put it on Google Cloud, or put it on your Android phone, or you can put it on iOS. Totally doesn't matter. You can take your model out of a developer's machine into production very easily by just using one command, export model, export saved model. OK, so you say, OK, Vikram, we built the model, but my model isn't good enough. I need this model to train even better and become much better. What do I do? So there are some things that we did in our model. Remember, there we used some constants right here. 64 units, 100 dimensions, 10 units. What are these? These are called hyperparameters. Hyperparameters are things right now which humans have to do to understand what is the best model out there. For that, we have a thing called hyperparameter optimization. What you do is you give it a range. You say, I want to go with 64 units to 600 units. I want to understand what is the best model architecture for me. So you give it a raw architecture and give it a range, and it tries to identify the best model in that architecture for your data. So that becomes hyperparameter optimization. And with that, it gives you back the model that is best for you. And you use that, and it keeps retraining on that. And there's a paper link for that if you want to understand that more. Google Cloud has very good functions on this. We'll talk about that in a minute. But you say, OK, Vikram, but my data is really large. It takes 15 days for me to train my model. What do I do? You can start using GPUs, but even then, my model takes now 7 days. What do I do now? For that, we have TPUs. TPUs are tensor processing units. Tensor processing units, we will show a demo, hopefully by the end, but they are way faster, like way faster. I have somewhere in the demo. The ResNet 50, which normally takes 15 days to train, takes less than an hour to train on TPUs. And like you can pass in state-of-the-art, it gives you state-of-the-art accuracy. It's not one pass. It's like multiple passes to understand that. And to do that, it's very easy. All the code that you wrote, it's exactly the same thing. Only thing you have to change is now use TPU-based functions. So we say TPU.cross shard operation and TPU estimator, rather than using normal estimator. That's it. That's all the change that you need to do. And this was before TensorFlow 2.0 is coming out. Once TensorFlow 2.0 is out, you hopefully don't have to even do that. Hopefully. Fingers crossed. All right. So what is TPU chip? TPU chip. This is TPU version 2. There's now TPU version 3 in the market already. TPU version 2 is similar to how your graphic cards work, but they are just more parallelized. They have reduced the amount of operations that it can do, but increased the amount of chips that it has. And they're able to do this all in a parallel computation. So that's why they can do it in a much faster way. We will show some stats on this by the end. All right. OK, now I have a good model. It's running, giving me good predictions. I have trained it multiple times, iterations over, and it's a big model now. How do I actually start using it? Up till now, not now, but Recently, what used to happen is you used to give this model to your dev team now. The DevOps team, it's the task of DevOps teams to find out how to serve this model. But with TensorFlow, we have one single API. You just export your saved model, and you pass it to TensorFlow serving. TensorFlow serving takes in your model, and you have an API endpoint. No need to do anything. No need to set up a Flask server, provide a storage space, storage location, and all those things. All gone. You take your model, and it's ready for serving, just by passing it inside a function. All right, it's good. I have the model on cloud, but I am a nomad. I don't want to be connected to internet all the time. What do I do now? OK, you can take your model on your phone. Use TensorFlow Lite. TensorFlow Lite will take your model, which is really huge, convert it into a smaller model with reducing the amount of data that it's storing, reducing the network, and now you can put that model inside a device. And you can even send this model across the channel. So if you have used Pixel 2's now listening feature or something like that, they update that data, update the model every few days. And do this all over the air. So model is so small that you can update it over the air. Generally, models are like GBs in size. Plus, this TensorFlow Lite works on all kinds of devices. So you can train it and convert it not only for Android devices to give you a Java API, but it also converts for C++ for iOS devices. And you can take it on a Raspberry Pi as well. So there you go. Now, TensorFlow supports all of these platforms, like almost all the popular architectures that you will find. Plus, it also supports all the languages. Not all, not fully, but almost all the languages. And I am very excited for JavaScript. So JavaScript will rule the world. So, just saying. So JavaScript is really important about that. And people who are web developers who don't have a lot of experience in using these things, they can take an existing model, deploy it onto their website, and they are already gone. There's no need for you to understand even half the things that are happening in the background. You can start using that right now. OK, all good. We have a model. Tomorrow, new data comes in. What do I do now? Do I retrain my whole model? Do I have to redo this whole thing again and every day? No, hopefully not. So everyone who has tried to do this, just say this, doing machine learning in production is hard. Because the reason it is hard is because whatever we talked about until now is just this, just that small piece in the whole puzzle. Your machine learning code is a very small piece in the whole puzzle. You have to collect the data. You have to do the feature extraction. You have to understand and worry about monitoring your pipelines and your data and your new model. You have to have analysis tools around it. How well your model is doing, how bad it is, what has the performance been between version 1 and version 2 and version 3, and serving infrastructure. Today you were in development, you're getting 10 requests an hour, now you're getting 10 requests a second. What are you going to do? You're going to scale up your systems and servers and all of those and worry about all of those. OK, so what about that? For that, until now, we used to have a specialized system for each algorithm. Every algorithm used to have a very special architecture built for them. For linear model, there's a different architecture. Deep neural networks, different architecture. And we are talking about machine architectures. But the promise of TensorFlow is you can use all different types of models using one single architecture. So that's how TensorFlow allows you to do that. Then let's talk about individual problems. Data collection. How do I solve data collection problem? For data collection, Google Cloud provides you various ways of doing that. If you have data which is streaming in real time, use Cloud Functions. If you have data which is streaming in real time but can be delayed, and you have to pass it to multiple sources, start using PubSub. PubSub is an event-driven data collection system. Then, if you have data which can be stored in tabular format, use BigQuery. BigQuery is one of the best data warehouses out there. It gives you storage on SQL-like query interface on really huge sets of data. There are blog posts out there where people are querying on terabytes of data within few seconds. So use BigQuery for any tabular data that you have. And then storage. Storage for any other kind of data, whether you have images, audio format, anything that you can store, storage can take it. Then feature extraction. For feature extraction, you can do that. You are aware about your features. But one thing that people generally miss is feature extraction during testing time is very different than doing that in development time. And while you are doing that in development versus production, it's very different. To do that, make sure that your development features are also available in production. You should use TF Transform. TF Transform gives you one way of extracting your features from your raw data and just using that same pipeline into production so that your models don't change, your variables don't change, your data type doesn't change. Then, for analysis of the model, we have a tool called Facets or something similar. I don't remember the name. We have links all there. And with that, you can analyze your model to understand how your model is doing between different versions without exporting it out. Next, feature enrichment. For feature enrichment, what are the tools that Google has? Google has data prep, where anybody who is just a normal person, you can go to data prep, you upload your data, it gives you ability to sort out your data and do all kinds of operations that you might want to do. Like it can take an address column and format and split it into days and columns and zip codes. Then there's data flow to build real-time pipelines and using Apache Beam. And if you're not familiar with data flow, if you're familiar with Spark, use Dataproc. Dataproc is already doing all the same things. I'm going to go quickly. Serving infrastructure and machine management. For that, two bigger problems that people were not dealing with until now. Continuous retraining. Continuous retraining is saying, today I have a model, tomorrow I need to retrain this model. For that, we have a lot of challenges that we need to deal with. But with Google Cloud, what it does is it provides all of these things for you, so the only thing you have to do is keep updating your data source. If you keep updating your data source, the rest of the triggers will take care of making sure your data gets updated, your model gets trained. After your model is trained, it will understand what is the difference between version 1 and version 2. You have to assign a threshold. You assign a threshold and saying that if version 2 is better than version 1 by this degree, then update my API. It will automatically do all of that for you. And then warm restarting. Warm restarting is saying, I have a huge model, it's running somewhere, but I don't use it until Monday morning at 9. That's the only time I need to use it. Monday morning, 9 to 11. But after that, my model needs to go down, shut down, and at 9, it should be ready for me to run. And Google takes care of this on machine learning engine for you. So you don't have to pay extra money to run all those servers all the time. It will automatically start the model and shut down the machines for you. OK, for training and serving, Google Cloud has Cloud Machine Learning Engine. And best of the hardware that you can use, GPUs are on Google Cloud from NVIDIA, and TPUs, Google's own proprietary hardware. OK, but I don't really, I shouldn't say this, but generally people don't really trust one cloud vendor. So what they end up doing is they want one way to do this across clouds. For that, you have TFX. TFX is TensorFlow's team trying to come up with tools that you can use across browsers, across vendors. And Kubeflow is a culmination of all of those tools into one single project, where it starts with Jupyter Notebook, and the whole cycle, all the tools that we talked about are all in there. Quickly going over this, components of production systems, this is a complete architecture, how you would want it to be. But this is where we don't have the slide. OK, we have most of those things already in place. There are a few things that are still missing, which are integrated job front end, which are available in Kubeflow now. So you can get started on that. OK, quickly, how does TensorFlow help you out with all of these? Flexibility of the model. Earlier, you had to build different architectures. Now you have TensorFlow, which can take all different types of data sets on all different types of models. You had to earlier retrain your model all the time, take one model, you discard it, discard the next model every iteration. Now you can pass the data forward, pass the learnings forward, and you have smaller amount of training time. We internally used to train one model for like hours, and now we take a few seconds to train a model from day 1 to day 2 to day 3, and it keeps getting better. Portability. TensorFlow provides you the ability to run it on your local, cloud, on device. You can train on Raspberry Pis as well. So you can take your model anywhere. And on your car, of course. Cars have GPUs now. You can run your data pipelines on Apache Beam. Apache Beam allows you to run it everywhere. Again, same thing. Direct runner on Google Cloud. You use Dataflow runner. On other servers, you can use Flink or anywhere else. Then your machine's configuration, how many machines you're using, how many ports you need for auto scaling, and everything else. You do that, all of that using Kubernetes. Kubernetes gives you Minikube on your machine, GKE on Google Cloud, Kubernetes cluster on any other cloud provider, and similar things. Then scalability. Earlier, up till now, user was training the model on their machine and throwing it over the wall to DevOps team. Now it doesn't have to be that. The models can easily transition. Both of the teams can test and come together and build your models and pass it forward. Interactive. Google has provided a lot of tools around TensorFlow on understanding your data, understanding your model. There are what-if tools, there are pair tools. And all of these things can help you understand better about your model. So what's next? Cloud TPUs. We talked about that. Cloud TPUs started with V2. Now they are on V3. 420 teraflops operations. That's a lot of operations. Plus, it's not just one thing. You can get a whole set of this, a whole cluster. And whole cluster is 11.5 petaflops. That's like pass a model and it's out already. So with 8 minutes of training time, ResNet 50, one of the biggest image models that is out there, gets trained with 93% accuracy in 8 minutes. This is the state of the art right now. Okay, what about building the models themselves? For that, we have neural architecture search. You have seen one presentation already about AutoML. There's been another one by Dan right there. What neural architecture search does, it applies this concept to give you AutoML, where it tries to find out the best model for you without you writing ever any code. You just pass in your data, it tries to identify the best model for you. The models that it gives you are very different, very complex, but you don't have to worry about that because you don't really care if it can give you the best model out there. And it performs better than your models, the handcrafted models, not only on small models, but also on large model sets. Okay, what do I suggest people to do? Add a pinch of magic, start with using others' model. If it doesn't work, craft your own models which are based upon the existing models, and use cloud to train all of these things. Coming in TensorFlow 2.0, we will have TensorFlow Keras, where you will start with packaged models. We will have distribution strategy to train your models. Once you have a model, save it onto a saved model, and then you can serve it on TF serving, JavaScript, Swift, TensorFlow, other clouds, anything. Get involved, TensorFlow org, that's community. Use collabs, they are free, they provide GPU, they provide TPU. It's available on Google Drive, you can save on GitHub as well. So don't worry about losing your stars. Anywhere you find that logo, run in Colab, just click on it, it goes on to Colab. And it provides you Jupyter-like interface. People who have seen the presentation that was before this presentation. If you want to learn on videos, youtube.com/TensorFlow. And if you want to read more about it, medium.com/TensorFlow, Twitter. And okay, finally, hopefully you have learned enough. If you have any questions, just so you don't do this, please ask questions, but I'll be outside. My time is over here. So thank you so much. Ask a question. Ooh, that was fast.